Right now, the Milky Way hurtles through space at over 1 million miles per hour towards something we cannot see. A wall of cosmic dust blocks the view, and behind it sits one of the most powerful gravitational forces ever measured. We will cross the hidden zone, trace the pull, map what's been buried for decades, and face the possibility that something enormous has been shaping our galaxy's path since the beginning. If you enjoy the journey, subscribe and leave a like. Now, prepare yourselves. We begin. The Milky Way is hiding something from us, and the hiding spot is built into the galaxy itself. Picture our galaxy from above. A flat, spinning disk of stars, gas, and dust stretching roughly 100,000 light-years across. We sit about 26,000 light-years from the center, tucked inside one of the spiral arms. From here, we can look outward in almost every direction and see billions of galaxies spread across the universe. Telescopes have mapped enormous structures hundreds of millions of light-years away. Astronomers have catalogued galaxy clusters, cosmic filaments, giant voids. The map of the universe is impressively detailed, except for one region, running like a thick belt around the entire sky, following the plane of our own galaxy, is a zone so packed with dust, gas, and stars that visible light from anything behind it simply cannot get through. Scientists call it the zone of avoidance. That name comes from the early days of galaxy cataloging, when astronomers literally had to skip that band of sky because nothing useful could be seen there. The dust scattered and absorbed light before it could travel the full distance to our telescopes. To understand how thick this wall is, imagine trying to read a book through 1,000 sheets of dark paper stacked on top of each other. The words are there. The light carrying them just never arrives. The dust in our galactic plane works the same way, absorbing optical light so completely that entire galaxy clusters on the other side are invisible to standard telescopes. The zone of avoidance covers roughly 20% of the entire sky, 1/5 of everything above us, completely obscured. For most of human history, we had no idea what was back there, and for a long time, astronomers assumed it was probably just more of the same ordinary galaxy clusters, similar to everything visible on either side of the band. That assumption held until the numbers stopped adding up. Scientists studying the motion of our galaxy noticed something strange. The Milky Way was not drifting randomly through space the way you might expect a galaxy to drift. It had a direction, a specific, measurable pull toward one part of the sky, and that part of the sky sat almost perfectly inside the zone of avoidance. The force moving us was enormous. Calculation after calculation confirmed it. Whatever was pulling the Milky Way, along with hundreds of neighboring galaxies, had to be something massive on a scale that had no confirmed match in the visible universe. Astronomers searched the regions they could see. They found concentrations of galaxies, yes, but nothing with enough gravitational muscle to account for the full observed motion. The answer had to be behind the wall. Here is what makes this so disorienting. Humanity has built telescopes that can detect the light of galaxies billions of light years away. We have instruments sensitive enough to capture the faint afterglow of the Big Bang itself. And yet a thick band of our own galaxy's dust was enough to hide whatever was pulling us through space. The dust is not spread evenly. It thickens toward the galactic center, creating a core region of near-total obscuration. Outside that core, the band thins slightly, and this is where radio telescopes and infrared instruments started to make progress. But the densest, most critical zone, the region directly aligned with the pull, remained stubbornly sealed. Astronomers kept pushing. They knew something was there. The motion of the Milky Way demanded it. And what they eventually found behind that wall was stranger than most of them expected. The first clue came from a number that refused to make sense. In the 1980s, a team of astronomers was studying the peculiar velocity of our galaxy. Peculiar velocity is the technical term for motion that cannot be explained by the simple expansion of the universe. Every galaxy moves outward as the universe expands, but some galaxies have an extra push or pull on top of that. The Milky Way had one. and it was significant. The team, later nicknamed the Seven Samurai, measured the motions of hundreds of elliptical galaxies across the sky. They used a method that compared how bright galaxies should appear based on their size versus how bright they actually appeared from Earth. The difference revealed real distances, and real distances revealed real velocities. The data pointed toward a region centered roughly in the direction of the southern constellation Centaurus. Our galaxy was moving toward that region at a speed of about 600 kilometers per second relative to the background radiation of the universe. To picture that, if you could drive a car at that speed, you would circle Earth in a little over a minute, and the entire Milky Way, with its hundreds of billions of stars and all their orbiting planets, was moving at that rate. Something had to be pulling it. Something with gravity powerful enough to drag an entire galaxy across millions of light years of space. The team calculated the mass required to generate that kind of pull. The number was staggering. Whatever was out there had to contain the mass of tens of thousands of galaxies compressed into a relatively concentrated region of space. Astronomers scanned that part of the sky carefully. They found galaxy clusters, yes, significant ones, but the visible mass fell short of what the motion required. The shortfall pointed straight into the zone of avoidance. This was the moment the problem became urgent. Astronomers were looking at a gravitational signature with no confirmed source. They named the source the Great Attractor, a placeholder for something enormous that the dust was blocking from view. The name stuck, partly because nothing better came along, and partly because it captured the scale of the mystery accurately. Confirming the Great Attractor required getting around the dust. Optical telescopes were useless in that direction. But dust is largely transparent to radio waves and to infrared light, which has longer wavelengths that can slip between dust particles without being absorbed. Teams began scanning the hidden zone using these tools. What they found changed the picture immediately. Behind the dust were galaxies, hundreds of them, then thousands. Dense concentrations of matter that optical surveys had completely missed. The zone astronomers had labeled as empty or irrelevant turned out to be packed with structure. One discovery stood out immediately. A massive cluster of galaxies sat almost exactly at the coordinates the motion calculations had predicted. Scientists named it the Norma Cluster. And even at first glance, it was clear this was a violent, dense environment, unlike most clusters visible in open sky. The motion data finally had something to point at. But as measurements improved, a deeper question surfaced. Was the Norma cluster itself enough to explain the full pull? Or was the Milky Way responding to something even farther back, even larger, still hidden deeper inside the obscured zone? The answer, when it arrived, made the Great Attractor look small. The Great Attractor is real, confirmed. A region of space with gravitational influence so vast it moves entire galaxy groups across hundreds of millions of light years. To understand what that means, you have to step back far enough to see the scale properly. Galaxies travel in groups. Our Milky Way belongs to the local group, a collection of roughly 80 galaxies spread across about 10 million light years. The local group belongs to a larger structure called the Virgo supercluster, a collection of galaxy clusters spread across about 100 million light years. And the Virgo supercluster, along with dozens of other superclusters, all sit inside an even larger structure called Laniakea. Laniakea stretches 500 million light-years across. It contains the mass of 100 million billion suns. And the entire thing, every cluster and filament and galaxy within it, flows gravitationally toward one central point. That point is the Great Attractor. Astronomers confirmed this by mapping the motion of galaxies across Laniakea and tracing every velocity back to its source. The result looked like rivers flowing toward a drain. Galaxies on the near side of the attractor moved toward it. Galaxies on the far side, which are being pulled back against the expansion of the universe, also moved toward it. Every vector pointed to the same location, in the direction of the Norma cluster, deep inside the zone of avoidance. The attractor region sits about 250 million light-years away. At the speed our galaxy moves, reaching it would take billions of years. But here is the strange part. we will never actually arrive. The universe is expanding, and the space between us and the attractor stretches faster than gravity can fully close the gap. We are falling towards something we will never touch. This creates an odd cosmic situation. The Milky Way moves through space under the influence of a gravitational anchor that keeps receding. The attractor pulls, the expansion pushes outward, and our galaxy traces a path shaped by both forces simultaneously. What sits at the heart of the attractor region is a massive concentration of galaxy clusters, dark matter, hot gas, and the gravitational sum of everything bound together. The Norma cluster is the most visible component. Around it, surveys have revealed additional clusters and filaments feeding into the same gravitational well. The whole region behaves like a cosmic drain, accumulating mass over billions of years. One critical fact confirmed by multiple independent studies: the Great Attractor is growing. Mass continues to fall into the region from surrounding areas of space. The concentration is denser today than it was 1 billion years ago, and denser still than it was 2 billion years ago. But here is where the picture gets complicated. When astronomers calculated the precise mass needed to produce the observed velocities across all of Laniakea, the attractor region came up short. The Norma cluster and its surroundings are massive, yes, enormously so. But the total gravitational accounting still left a gap. Something beyond the attractor was also pulling, something farther away, behind the attractor itself, adding its gravity to the motion and bending the trajectory of our entire supercluster. Scientists knew they had to look deeper, past the Great Attractor, past the zone of avoidance, into a region of space even more obscured and even less mapped than anything they had studied before. What they found waiting there was a structure that dwarfed the attractor completely. The Great Attractor sits at roughly 250 million light-years from Earth. The zone of avoidance cuts across the sky in a band about 20 degrees wide on each side of the galactic plane. The coordinates of the attractor place it squarely inside the densest part of that obscured band. The overlap is almost exact, and that overlap is the reason it took until the 1980s to even confirm the attractor existed. This alignment created one of the most frustrating situations in modern astronomy. The most powerful gravitational influence on our galaxy, a force strong enough to redirect an entire supercluster of galaxies, happened to sit in the one part of the sky where our own galaxy blocked the view. As if a city built its observatory next to the only mountain in the region, and the one thing worth studying was hidden directly behind the peak. Astronomers had to ask, was this coincidence, or was the alignment telling them something? The answer is geometry, confirmed. Our solar system sits inside a spiral arm of the Milky Way. The galactic plane, the flat disk of the galaxy, extends around us in all directions. Because we are embedded inside the disk, looking along the plane means looking through the maximum amount of dust and gas. Any large-scale structure in the universe that happens to sit in that direction from our vantage point will be obscured. The Great Attractor did not position itself behind the dust. Our position inside the galactic disk placed the dust between us and the attractor. A civilization living above or below the galactic plane, outside the disk entirely, would have a clear view of the attractor region, with no obscuration at all. This is a profound limitation. Our perspective, our specific address inside the Milky Way, determines which parts of the universe we can easily study. And the universe distributed its most gravitationally significant nearby structure into precisely the zone our position makes hardest to observe. The consequences of this alignment stretched across decades of research. Galaxy catalogues built before radio and infrared surveys had a blind strip running through them. Calculations of large-scale structure, of how matter was distributed across the universe, had a gap baked in. Models built to explain cosmic motion had to treat the attractor region as a rough estimate rather than a confirmed measurement. Even today, with infrared and radio instruments capable of piercing most of the dust, the very center of the zone of avoidance near the galactic core remains partially obscured, The densest dust concentrations absorb even infrared light at sufficient depths. Some pockets of the hidden zone are still genuinely invisible to every instrument currently in operation, and the Great Attractor sits close enough to that core region that its full structure, the complete shape of its mass distribution, remains incompletely mapped. The dust did not hide everything, but it hid enough to delay the discovery of a force that has been shaping our galaxy's path through space for billions of years. What changed the situation was a different kind of light entirely. Infrared telescopes, looking at wavelengths longer than visible light can reach, began picking up the heat signatures of galaxies buried inside the dust. And what those telescopes revealed behind the wall was a level of crowding, a density of galaxies that nobody expected to find. Infrared light travels differently than visible light. Where visible wavelengths scatter off dust particles and get absorbed, infrared wavelengths slip through. Dust is mostly transparent to them. Point an infrared telescope at the zone of avoidance, and the wall that blocks optical instruments becomes significantly thinner. When astronomers did exactly that, beginning seriously in the 1990s and accelerating through the 2000s, the hidden zone opened up. The first systematic infrared survey of the zone of avoidance came from a satellite called the Infrared Astronomical Satellite, launched in 1983. Its data revealed galaxies behind the dust wall that had never been catalogued, thousands of them. The zone that early astronomers had skipped over and labeled as empty space turned out to be filled with structure. Follow-up surveys refined the picture dramatically. The 2-micron all-sky survey, completed in 2003, was the most thorough infrared mapping of the full sky ever produced at that point. It detected approximately 1 million galaxies behind the zone of avoidance that optical telescopes had completely missed. The shape of the large-scale structure on the hidden side of the sky began to emerge from the data. What the infrared data revealed was striking in its density. The region surrounding the Great Attractor was crowded. Galaxy clusters packed close together, connected by filaments of galaxies stretching between them, with concentrations of mass at the intersections. The hidden zone did not contain empty space with a single massive cluster sitting alone. It contained an environment as rich and complex as anything visible in the open sky. One specific feature stood out immediately. The infrared surveys showed that the galaxy density in the attractor region was significantly higher than the density in surrounding areas. Mass was genuinely concentrated there, not just nearby. The Great Attractor was not a gravitational ghost. It had real, physical substance spread across hundreds of millions of light years. Infrared data also allowed astronomers to measure redshifts, the stretching of light that reveals how fast a galaxy is moving away from us, and therefore how far away it is. With redshift measurements, the three-dimensional structure of the hidden zone became visible for the first time. Clusters at different distances could be separated. The attractor region could be mapped in depth, not just across the sky. The picture that emerged showed layers, closer structures, farther structures, all moving in the same gravitational flow. And behind the attractor region, at greater distances, the infrared data hinted at something even larger contributing to the pull. But infrared surveys have limits. They reveal the location of galaxies, but they cannot fully penetrate the densest central strip of the galactic plane, where dust reaches its maximum thickness. The exact core of the zone of avoidance, a strip a few degrees wide running along the galactic equator, remains resistant even to infrared instruments. Radio surveys pushed into that strip next. Radio waves pass through dust almost entirely unobstructed. Hydrogen gas in distant galaxies emits at a specific radio wavelength, and that signal carries through the dust wall regardless of how thick it is. Radio surveys of the hidden zone began confirming galaxies even inside the densest dust corridor, and they began sketching the outline of a structure inside the attractor region that would eventually be given a name, the Norma Cluster. The wall had broken open, and behind it was a city unlike anything astronomers had catalogued before. The Norma Cluster is approximately 220 million light-years away, sitting inside the zone of avoidance near the heart of the Great Attractor region. Once infrared and radio instruments made it visible, astronomers realized they were looking at one of the densest concentrations of galaxies within the nearby universe. A galaxy cluster is exactly what it sounds like, a massive collection of galaxies gravitationally bound together, orbiting a common center of mass, surrounded by a vast cloud of superheated gas and filled with dark matter. Most clusters contain hundreds of galaxies. The largest contain thousands. The Norma cluster sits toward the high end of that scale, and its environment reflects it. Inside a cluster this dense, galaxies do not drift peacefully. They move at speeds of thousands of kilometers per second relative to one another. Collisions are common over cosmic timescales. When two galaxies collide inside a cluster, the result is not a quiet merger. Gas clouds slam together at enormous velocities, triggering explosive bursts of star formation. Stars from both galaxies scatter into new orbits. The shape of both galaxies distorts, stretches, and eventually dissolves into a new, combined structure. The Norma cluster hosts this kind of activity across dozens of interacting systems simultaneously. X-ray telescopes, which detect the heat of gas compressed between colliding galaxies and clusters, have imaged the Norma cluster as a churning environment of superheated plasma. The gas between galaxies glows at tens of millions of degrees, visible only to instruments sensitive to the high-energy end of the electromagnetic spectrum. One specific feature of the Norma cluster has attracted sustained scientific attention. Astronomers detected signs of a subcluster merger in progress. A smaller cluster of galaxies is falling into the Norma cluster, compressing the hot gas between them into a shock wave that spans millions of light-years. This kind of merger event releases energy comparable to the most powerful explosions in the universe, though spread across an enormous volume of space over millions of years. The Norma cluster also sits at the intersection of multiple galaxy filaments. Filaments are the spine-like threads of the cosmic web, long chains of galaxies and dark matter stretching between clusters and superclusters. Several major filaments feed into the Norma cluster from different directions, channeling matter toward it continuously. The cluster grows as material flows in along these highways. At the center of the Norma cluster sits a massive elliptical galaxy, significantly larger than the Milky Way. Elliptical galaxies at cluster centers tend to grow by cannibalizing smaller galaxies that fall too close. Over billions of years, this central galaxy has absorbed the mass of many former neighbors, growing into one of the largest single galaxies in the nearby universe. For a long time, astronomers treated the Norma cluster as the Great Attractor itself, the final answer to where the pull was coming from. The cluster was massive enough to produce significant gravitational influence, and its location matched the direction of our motion. Then, better measurements came in, and the simple explanation fell apart. The Norma cluster, for all its violence and mass, could account for only a portion of the observed pull on our galaxy. The full velocity of the Milky Way and its neighbors required something more. Something farther away was adding its gravity to the equation, and it had been hiding even deeper inside the dust. The Milky Way is not sitting still. No galaxy does. But our galaxy's motion carries a specific urgency that sets it apart from simple universal expansion. Start with the basics. The universe expands. Every galaxy moves away from every other galaxy as space itself stretches. This motion does not require a source. It is built into the fabric of the universe since the Big Bang. Astronomers account for this expansion in every velocity measurement they take. What they cannot account for so easily is the extra motion on top of expansion. The Milky Way moves toward the Great Attractor region at roughly 600 kilometers per second relative to the cosmic microwave background, the ancient light left over from the Big Bang that fills the universe uniformly in all directions, 600 kilometers per second, every second, in a specific direction. To put that in terms that register physically, the distance from Earth to the Moon is about 240,000 miles. At 600 kilometers per second, the Milky Way covers that distance in roughly 10 minutes. In a single day, our galaxy moves about 32 million miles through space toward the attractor region. In a year, it crosses a distance greater than the full stretch from Earth to the outer edge of the solar system many times over. And the Milky Way is enormous. Its disk spans 100,000 light-years. It contains somewhere between 200 and 400 billion stars. Every single one of those stars, every planet orbiting them, every cloud of gas drifting between them, all of it moves together at this speed. The entire structure, moving as one object. Scientists confirmed this motion by measuring what is called the dipole anisotropy of the cosmic microwave background. The ancient light from the Big Bang hits Earth's detectors slightly more energetically from the direction we are moving toward, and slightly less energetically from behind. The difference is small but measurable, and it reveals our true velocity through space with remarkable precision. Our galaxy is not the only thing moving. The entire local group of galaxies moves at roughly the same speed in the same direction. The Virgo cluster, which anchors a much larger region of space, also participates in this flow. Looking further, the motion extends across the full breadth of Laniakea, the 500 million light-year supercluster of which we are a part. Everything inside it streams toward the attractor region. Here is what gives that motion its weight. The Milky Way has been moving at this speed for billions of years. It will keep moving for billions more. And despite covering these enormous distances each year, the attractor region remains hundreds of millions of light-years away. The scale of the universe absorbs our velocity the way an ocean absorbs a stone. The question astronomers kept asking was simple. What is massive enough to maintain this pull across such enormous distances? What object or region of space generates a gravitational force large enough to move a supercluster? The Norma cluster answered part of it, but only part. In 2014, a team reanalyzed galactic motion data with new precision, and buried in the numbers, in a region of sky, even deeper inside the zone of avoidance than the attractor itself, they found a second signal, a second hidden giant. In 2017, astronomers announced the discovery of a supercluster of galaxies that had been sitting inside the zone of avoidance, invisible for the entire history of modern astronomy. They called it the Vela supercluster. The discovery came from a years-long survey using optical and radio telescopes specifically designed to peer through the dust at the edges of the hidden zone. The survey team mapped galaxies in a region of sky that previous catalogues had left largely blank. What emerged from the data was a massive concentration of galaxies spread across a region of space, roughly 800 million light-years from Earth. The Vela supercluster spans roughly 300 million light-years across. It contains the mass of tens of millions of typical galaxies, and its position in the same general direction as the Great Attractor but farther away and slightly offset, meant it had been adding its gravitational pull to our galaxy's motion without anyone knowing it. When researchers added the Vela supercluster's gravitational contribution to their models of the Milky Way's motion, the numbers improved significantly. Some of the remaining discrepancy between observed velocity and known gravitational sources closed up. The hidden giant had been part of the equation all along, invisibly shaping the path of the Milky Way. The Vela supercluster is particularly interesting because of where it sits in the galactic plane. Its center falls inside the zone where optical surveys are completely blocked. Only by combining radio data, infrared observations, and spectroscopic measurements of individual galaxy velocities did the full structure become visible. The supercluster announced its presence through the motion it caused before any instrument could directly image it. This discovery revealed something important about the broader problem. The zone of avoidance was hiding multiple significant structures simultaneously. The attractor region, the Norma cluster, and now the Vela supercluster were all stacked behind the same dust wall, each contributing gravity, each previously unknown or underestimated. And the discovery raised an immediate question. If two major structures had hidden inside the blind spot, were there more? The answer, based on what the motion data continued to imply, was yes. When astronomers modeled the full large-scale flow of galaxies around the attractor region, including the Vela supercluster's contribution, they still could not fully account for the observed motion. The velocity budget still had a gap. Something with even more mass, at even greater distances, was pulling. The search led scientists to turn their attention not deeper into the zone of avoidance, but farther back behind it, past the attractor, past Vela, into a region so remote that even the dust became less of a problem at those distances, because the structures were large enough to be partially detectable around the edges of the obscured band. What they found there had a name already. Astronomers had catalogued it years earlier from the visible parts of the sky. They simply had not understood yet how massive it was, or how far its gravitational reach extended. It was the largest concentration of matter within 1 billion light-years, and it was pulling everything, including the Great Attractor itself. The Great Attractor felt like the final answer when astronomers first identified it. A massive concentration of galaxies, confirmed through infrared and radio surveys, sitting in the direction our galaxy was moving. The math was close enough. The discovery was dramatic enough. For a while, the case seemed closed. Then the measurements got better, and the gap between observed and explained became impossible to ignore. Here is the core problem. Calculating how much gravity a structure generates requires knowing its mass. Knowing its mass requires knowing how many galaxies it contains, where they are, and how much dark matter fills the space between them. In the zone of avoidance, all of those measurements carry uncertainty because the dust obscures the full picture. Early mass estimates for the attractor region were rough approximations built from incomplete data. As surveys improved, the estimated mass of the attractor region rose. More galaxies were detected, more clusters were confirmed. Dark matter maps, built from the gravitational lensing of background objects, added additional mass to the count. But the observed velocity of the Milky Way also grew more precise, and the precise velocity consistently exceeded what the improved attractor mass estimates could explain. Scientists ran simulations. They modeled the attractor region with every confirmed galaxy cluster and dark matter concentration accounted for. They ran the models forward and backward in time, checking whether the predicted motion matched the observed motion. Every simulation came back with the same result. The attractor explains a significant fraction of our motion, somewhere between 40 and 60% depending on the model. The rest of the motion comes from somewhere else. Some of it comes from the Vela supercluster, confirmed after its discovery in 2017. Some of it comes from the dipole repeller, a giant void that pushes our galaxy from the opposite direction, which gets addressed shortly. But even after adding those contributions, residual motion remained in the models. Astronomers began looking at an even larger structure farther behind the attractor, a structure that had been sitting in the visible part of the sky for decades, without anyone realizing how dominant its gravitational influence really was. This structure was not hidden by dust. It was hidden by distance, and by the fact that nobody had mapped it comprehensively enough to understand its full mass until very recently. The surveys that finally revealed its true scale placed it among the most massive concentrations of matter in the observable universe. And when its gravitational contribution was added to the models, something remarkable happened. The velocity gap closed significantly. The Milky Way's motion, measured against the cosmic background with precision instruments, finally made sense. The full budget of gravitational forces pulling and pushing our galaxy through space added up to something approaching the observed number. But approaching is not the same as matching. A gap remained, a small one, within the margin of measurement error, or possibly a real discrepancy pointing at something not yet found, something even farther back, something the surveys have not fully resolved, something that might require an entirely different class of structure to explain. Before going there, you have to understand what the Shapley supercluster is, because nothing in the nearby universe prepares you for its scale. The Shapley supercluster sits about 650 million light-years away. It is the most massive concentration of matter in the nearby universe, meaning within the 1 billion light-year bubble of space that astronomers can map in detail. Its scale is difficult to compress into any single comparison, The supercluster spans roughly 350 million light-years across. It contains the mass of approximately 10 million billion suns. It holds dozens of individual galaxy clusters, packed into a region of space, far denser than the surrounding cosmic web, with a core concentration called the Shapley core that is among the most gravitationally extreme environments known. Astronomer Harlow Shapley noticed this region of sky in the 1930s. He observed an unusual concentration of galaxies in the direction of the Centaurus constellation. But with the instruments of that era, he could only see that the region was unusually rich. He could not measure its full extent or understand its mass. It took decades of improved surveys to reveal the full structure. By the late 1990s, astronomers had mapped enough of the supercluster to estimate its mass and its distance. What they found was sobering. The Shapley supercluster was so massive that its gravity extended far beyond its physical boundaries, reaching out across hundreds of millions of light-years and contributing a measurable gravitational pull on everything within that range, including us. The Milky Way sits roughly 650 million light-years from the Shapley supercluster's core. Gravity follows an inverse square law, meaning it weakens dramatically with distance. At 650 million light-years, the pull from any single cluster would be negligible. But the Shapley supercluster contains so many clusters, so much mass, spread across so large a volume, that even at that distance, its combined gravitational influence registers measurably on our galaxy's motion. Studies published in the early 2000s calculated that the Shapley supercluster contributes roughly 20 to 25% of the total gravitational pull moving the Milky Way toward the attractor region. It is pulling us from behind the great attractor, adding its force to the overall motion in the same direction. The Shapley supercluster is also itself moving. Everything on the scale of superclusters participates in the large-scale flow of the universe, drifting toward even more massive concentrations of matter at greater distances. The Shapley supercluster is massive enough to be partially responsible for the flow of galaxies near it, while simultaneously being pulled by structures at distances we have barely begun to map. One key point confirmed by multiple research groups: the Shapley supercluster existed in something close to its current form early in cosmic history. Structures of this mass take an extraordinarily long time to assemble. Models of the early universe suggest that a concentration like Shapley required nearly the full age of the universe to accumulate the mass it now contains. That timeline has its own implications. If the Shapley supercluster has been this massive for billions of years, it has been pulling the Milky Way for billions of years. Our galaxy's trajectory through space has been shaped by this distant anchor for longer than complex life has existed on Earth. And yet the Shapley supercluster, as massive as it is, may itself be responding to something even larger and more distant, something that sits at the very edge of our mapping ability and possibly beyond it. Scientists did not discover the great attractor and then measure our motion. The motion came first, the source came second, and that sequence carries a consequence most people overlook. When astronomers first began accurately measuring the peculiar velocity of the Milky Way in the 1970s, they were using a tool they had not expected. The cosmic microwave background had been discovered in 1965, the ancient light left over from the Big Bang filling the universe uniformly in all directions. Teams studying this background radiation noticed something subtle. The light was slightly more energetic from one direction, slightly less energetic from the opposite direction. This tiny asymmetry, called the dipole anisotropy, revealed that Earth was moving through the universe at a measurable velocity relative to that background. Since Earth moves with the Sun moves with the galaxy, and the galaxy moves with the local group. What the measurement actually captured was the total motion of the entire local group through space. The velocity was striking, roughly 600 kilometers per second, directed toward the constellation Centaurus. And it was already there, fully established, before anyone had identified what was causing it. This sequencing matters because it means the gravitational influence on our galaxy is old. The attractor region has been pulling the Milky Way for a very long time, billions of years. long enough for our galaxy to travel enormous distances under that influence while remaining far from the source. Cosmological models confirmed this. Simulations of galaxy formation that include realistic distributions of dark matter and galaxy clusters consistently produce motion patterns similar to what we observe. The attractor formed early, growing from initial density fluctuations in the early universe. As it grew, its gravitational reach extended further, pulling in neighboring galaxies and clusters that had been moving more freely before. The Milky Way's current trajectory is the accumulated result of billions of years of gravitational steering. Every early universe condition, every cluster that formed near us, every void that opened up around us, contributed to the path our galaxy now follows. One implication of this long history stands out. If the attractor has been pulling us for that long, and if additional structures like the Vela supercluster and the Shapley supercluster have been adding their gravity throughout, then our galaxy's position today is not random. The Milky Way is where it is, inside Laniakea, inside this particular region of the cosmic web, partly because of gravitational forces that have been shaping its path since the universe was young. That raises a question with real stakes for understanding the cosmos. If gravity has been steering galaxies for billions of years toward the attractor, what does the structure look like today at the core? How dense has it become? How many galaxies have already fallen in? And what does the core of the attractor region look like from the inside? The answer requires looking at the Norma cluster again, more carefully this time. Because inside that violent cluster, astronomers found evidence of something ancient and massive that had been growing long before the first survey ever pointed in that direction. Something that connects the entire story to the one kind of signal no optical or infrared instrument can see. But that tells us more about the hidden structure than almost anything else. The cosmic microwave background is the oldest light in the universe. It was released about 380,000 years after the Big Bang, when the early universe cooled enough for atoms to form and light to travel freely for the first time. That light has been traveling ever since, spreading across the universe, stretching as space expands, and filling the sky with a faint, uniform glow. It is almost perfectly uniform. But only almost detailed maps of the cosmic microwave background reveal tiny fluctuations in temperature, patches that are slightly hotter or slightly cooler than the average. These fluctuations were imprinted in the early universe by density variations, regions where matter was slightly more or less concentrated. They seeded everything that came after: the galaxies, the clusters, the superclusters, the entire large-scale structure of the universe today. One anomaly in those maps has resisted explanation for 2 decades. Astronomers call it the cold spot. The cold spot is a region of the cosmic microwave background significantly colder than the surrounding temperature. Its size is roughly 30 degrees across on the sky, which sounds small but is enormous in terms of actual angular area on the full sky map. It sits in the southern hemisphere sky, in the direction of the constellation Eridanus, and its statistical improbability, given standard models of the early universe, is significant enough that multiple papers have been dedicated to explaining it. One of the most compelling explanations involves a supervoid, a region of space with far less matter than average, so large that light passing through it loses a measurable amount of energy. When light from the cosmic microwave background travels through a region of unusually low density, it has to climb out of a gravitational landscape that is less deep than expected, and it loses energy doing so. That energy loss shows up as a cold spot on the temperature map. Here is where the connection to the blind spot becomes significant. The direction of the cold spot on the sky overlaps with the general direction of the large-scale gravitational flow that includes the Great Attractor. The supervoid, hypothesized to produce the cold spot, if it exists, sits in a region partially obscured by the zone of avoidance. A supervoid of the required size would be roughly 1 billion light-years across. That would make it one of the largest confirmed voids in the observable universe. And its position in the direction of our motion raises an unresolved question. If a void of that scale exists in that direction, how does it interact with the gravitational pull of the attractor region? The two effects pull in opposite directions. A supervoid pushes galaxies toward its edges, away from its center. The attractor pulls galaxies toward its core. If both exist in similar directions from our position, they could partially cancel each other out, or their combined influence could produce the complex flow pattern astronomers have been struggling to model. Confirmed fact: the cold spot is real. Confirmed, it is statistically unusual. A specific supervoid of the required size has been partially detected, but remains unconfirmed. The full picture requires data from regions that sit, once again, inside the zone of avoidance. The blind spot keeps inserting itself into every attempt to understand the forces shaping our galaxy's path. And one of the strangest signals coming from that blind spot has no confirmed explanation at all. Astronomers do not only look at visible light or infrared wavelengths when studying the zone of avoidance. Radio telescopes have scanned the hidden zone systematically for decades. X-ray satellites orbiting above Earth's atmosphere have mapped the sky across the hidden band, and both types of instruments have found signals that complicate the picture. Some of those signals have been explained. Radio emissions from galaxies hidden behind the dust. X-ray glows from the hot gas surrounding confirmed clusters. The expected signatures of known astrophysical processes operating inside the obscured zone. These are expected, and identifying them through the dust has been one of the main ways astronomers have confirmed the presence of structures like the Norma cluster. But not all the signals match known catalogs. Radio surveys of the galactic plane have identified sources inside the zone of avoidance that do not correspond to any confirmed galaxy, cluster, or astrophysical object in existing catalogs. Some of these could be foreground objects, something inside our own galaxy producing the emission rather than something behind the dust wall. Separating galactic foreground signals from extragalactic background signals is one of the core technical challenges of studying the hidden zone. Others remain genuinely unidentified. Radio telescopes have logged point sources and extended emission regions inside the zone of avoidance that multiple follow-up observations have failed to fully classify. In some cases, the emission profile matches what a distant galaxy cluster would produce, but no optical or infrared counterpart can be confirmed because the dust is too thick. X-ray observations add another layer of complexity. The Röntgen satellite, which conducted the first full-sky X-ray survey in the early 1990s, detected X-ray emission from multiple regions inside the zone of avoidance. Some of this emission maps onto confirmed clusters like the Norma cluster, but diffuse X-ray emission from extended regions, spread across angular scales larger than any single known cluster, has been detected in areas where the hidden source remains unclear. Diffuse X-ray emission of that kind typically indicates hot gas at millions of degrees spread across tens of millions of light years. The only structures capable of heating gas to those temperatures across those distances are large galaxy clusters, or superclusters, in the process of merging or accumulating mass. If the X-ray emission from certain parts of the hidden zone is extragalactic, it could be tracing the hot gas envelope of a massive structure that has not yet been fully identified, a structure that does not appear in any catalogue because nobody has been able to resolve it cleanly from behind the dust. Current instruments cannot definitively confirm or rule out this possibility. The next generation of X-ray space telescopes, with significantly better angular resolution and sensitivity, may change that. What is confirmed? The hidden zone contains X-ray and radio sources that remain unclassified. What is a credible theory? Some of these sources trace a structure or structures of significant mass that current surveys have not fully resolved, and the unclassified signals do not stand alone. Dark matter maps of the hidden zone, built from entirely different measurements, tell a story that overlaps with the radio and X-ray data in ways that are difficult to dismiss as coincidence. A supervoid is one of the emptiest regions of space possible, a volume of the universe where galaxy density falls far below the cosmic average, sometimes by 80 or 90%. Supervoids are not small. The largest confirmed supervoids span hundreds of millions of light-years. Gravity works in both directions. Matter pulls toward concentrations, away from those concentrations. In regions of very low density, the opposite effect operates. Galaxies near the edge of a supervoid get pushed outward as the expansion of the universe accelerates inside the void faster than in the denser surrounding regions. This push has been measured for confirmed supervoids, and it contributes to the large-scale motion of galaxies in the vicinity. The hypothesis of a supervoid behind the zone of avoidance, in the direction opposite to the great attractor, has been discussed in the scientific literature as a possible contributor to our galaxy's motion. If a supervoid sits behind us, in the direction away from the attractor, it could push our galaxy forward toward the attractor region, adding a repulsive component to the gravitational pull. This would mean our motion is shaped by two forces simultaneously: a pull from the attractor ahead and a push from a void behind. Astronomers identified a confirmed version of exactly this dynamic in 2017, when researchers published evidence for the dipole repeller. The dipole repeller is a large, underdense region located in the general direction away from the great attractor. Its existence, confirmed through careful mapping of galaxy velocities in the surrounding region, showed that our galaxy was being pushed away from a void at roughly the same rate it was being pulled toward the attractor. The two forces combined explain our motion more completely than either alone. But a larger supervoid, hypothetically behind the zone of avoidance itself and partially overlapping with the direction of the dipole repeller, could amplify this effect. Its size and position would need to be precisely measured to calculate its contribution. And measuring a supervoid inside the zone of avoidance faces the same basic problem as measuring anything else there. The dust blocks the view. Indirect evidence for such a void can be gathered from the large-scale motion of galaxies in the surrounding regions. If a supervoid exists behind the dust wall, the galaxies near its edges should show a characteristic outward motion, streaming away from the void's center. Velocity surveys of galaxies around the edges of the zone of avoidance have been used to search for exactly this pattern. Some surveys have found hints of such motion. The data is consistent with a low-density region behind the dust, contributing a modest push to the overall flow. But the signal is below the threshold of confident confirmation with current data. A supervoid of sufficient size in that location would also affect the cosmic microwave background. Light passing through a large void loses energy, producing a cold spot. The cold spot in the direction of Eridanus, discussed earlier, remains one of the candidate explanations for a supervoid, and its direction partially overlaps with the region behind the zone of avoidance. Two unconfirmed structures, one cold spot, one unexplained motion budget, all pointing toward the same obscured region of sky. The physics of push and pull behind the blind spot is deeply connected to whether the universe itself is shaped the way our standard models predict. The standard model of cosmology makes a specific prediction about how large structures in the universe can grow. Gravity is slow. The universe has only been around for about 13.8 billion years. In that time, gravity can pull matter together into clusters and superclusters, but there is a size limit. Structures above a certain mass, assembled within the age of the universe, should be extraordinarily rare or impossible depending on the scale. That limit has been tested repeatedly, and several observed structures push against it. The Shapley supercluster, confirmed as a real concentration of mass, sits at the edge of what standard models comfortably allow. Researchers who have modeled Shapley's formation history find that assembling its mass within the age of the universe requires an unusually favorable set of initial conditions. The supercluster exists, but its existence is statistically improbable within the standard framework. Now, consider what happens if a structure significantly larger than Shapley exists inside or behind the zone of avoidance. A structure assembled early, possibly fed by an unusually dense region of the early universe, that has been growing for billions of years without being fully detected. Such a structure would serve as a gravitational anchor for everything around it. Galaxies, clusters, superclusters, all would orient their motion toward this anchor over billions of years. The large-scale flow of the Laniakea supercluster the streaming of galaxies toward the attractor region, and the pull we attribute to the great attractor could all be downstream effects of this single, deeper concentration. This is a theoretical possibility, not a confirmed discovery, but it is grounded in real physics. Density variations in the early universe did produce some regions that were significantly denser than average. These dense seeds grew fastest under gravity, assembling the largest structures first. If one such seed happened to sit in the direction of our current motion, and if that seed was unusually large, it could have spent billions of years assembling a structure that current surveys have not yet characterized. Cosmologists have explored this scenario in simulation. They run models of the early universe with density fluctuations calibrated to observations, then fast forward to the present and check whether structures of the required mass can appear in the zone of avoidance region. Some simulations produce candidate structures, others do not. The results depend sensitively on the exact distribution of initial density fluctuations, which current measurements constrain but do not pin down perfectly. The key uncertainty is the zone of avoidance itself. If the missing mass required to explain our motion sits inside the hidden zone, no model can be definitively confirmed or ruled out without resolving the dust problem. What makes this possibility more than idle speculation is the X-ray data, the dark matter maps, the radio signals, and the unresolved velocity budget, all of which independently point towards something significant in the hidden zone. Each line of evidence carries its own uncertainties, but they all point the same direction. If a megastructure does sit behind the blind spot, it formed early, it grew for most of the age of the universe, and it has been the dominant gravitational influence on our galaxy's path for longer than Earth has existed. The question of whether that structure exists, and how large it is, may hinge on something that has nothing to do with the zone of avoidance directly: the way dark matter arranges itself in space. Dark matter cannot be seen. It does not emit light, absorb light, or interact with light in any way that telescopes can detect. Astronomers know it exists because of what it does to everything around it. Its gravity bends light from distant galaxies through a process called gravitational lensing, and by measuring how much bending occurs in different parts of the sky, scientists can map where the dark matter concentrates. This method works even through the zone of avoidance. Dust obscures visible and infrared light from galaxies, but the bending of light by dark matter is a geometric effect. It does not require looking through the dust at the hidden region. It requires looking at galaxies on the far side of the sky and measuring how their light bends as it passes through the dark matter distribution between us and them. Dark matter maps, built from lensing surveys, reveal a different picture of the attractor region than visible or infrared galaxy surveys alone. Galaxies trace dark matter, but imperfectly. The dark matter distribution is smoother, more extended, and often more massive than the galaxy distribution suggests. In the direction of the zone of avoidance, lensing-based dark matter maps show concentrations that extend beyond the boundaries of confirmed galaxy clusters. The mass inferred from lensing in some parts of the hidden zone exceeds what the galaxy counts would predict. This excess suggests that either the galaxy surveys are undercounting the galaxies in those regions, which is plausible given the dust obscuration, or that the dark matter distribution there is genuinely more concentrated than the visible structure indicates. Crucially, some of the highest dark matter concentrations in the lensing maps overlap with regions inside the zone of avoidance where unclassified radio and X-ray signals have been detected. The convergence is not proof of a hidden megastructure, but it builds a coherent picture. High dark matter density, unusual radio emission, diffuse X-ray glow, and unresolved velocity budget, all concentrated in the same general direction. The dark matter maps also reveal what astronomers call the cosmic web scaffold in the hidden zone. Filaments of dark matter extend between the confirmed clusters visible on either side of the hidden band, threading through the obscured region and connecting structures across the dust wall. These filaments channel ordinary matter along their length, feeding clusters at the intersections. If a large concentration of dark matter sits at the intersection of multiple filaments inside the zone of avoidance, it would accumulate ordinary matter over time, grow, and generate the gravitational influence implied by the motion data. The dark matter scaffold would be there first, pulling in gas and galaxies, building a structure that the dust wall currently prevents us from seeing directly. The lensing measurements in the zone of avoidance are not as precise as they are in open sky regions. Fewer background galaxies are visible through the dust, so the lensing statistics are noisier. But the signal is there, and it points consistently toward excess mass in the hidden zone. Understanding the relationship between the dark matter scaffold and the gravitational pull on our galaxy requires one more piece of the puzzle: the force pushing from behind, a force that comes from emptiness rather than mass. For decades, the story of our galaxy's motion was told entirely in terms of attraction. The Great Attractor pulls. The Shapley supercluster adds to the pull. The motion of the Milky Way results from gravity drawing it forward. Then, in 2017, a team of astronomers published a paper that reframed the entire picture. They called the new discovery the dipole repeller. The dipole repeller is a giant, underdense region of the universe, a supervoid, located in the general direction opposite to the Great Attractor on the sky. Its center sits roughly 600 million light-years away, in the direction of the constellation Perseus and the surrounding region of sky. And rather than pulling our galaxy, it pushes it. The pushing mechanism is subtle but real. Inside a supervoid, the expansion of the universe accelerates. There is less matter to slow the expansion down. Galaxies near the edges of a supervoid experience an outward pressure, pushed away from the void's center as the space inside it expands faster than average. This is sometimes called the anti-gravity of voids, though it is more precisely the effect of the universe's accelerating expansion being less constrained in low-density regions. The team that discovered the dipole repeller mapped the three-dimensional velocity field of thousands of galaxies across a large volume of space surrounding the Milky Way. They built a model of all the gravitational influences from known mass concentrations and compared its predictions to the actual galaxy velocities. The model consistently underpredicted the velocity of our galaxy and its neighbors toward the attractor. Adding the dipole repeller solved the discrepancy significantly. A low-density region of the required size and position, pushing our galaxy away from its center, contributed roughly half the total observed motion when combined with the pull of the attractor and Shapley. Our galaxy's path through space results from both a massive push from behind and a massive pull from ahead. This discovery changed how cosmologists think about large-scale motion. Galaxy flows are shaped by overdensities and underdensities simultaneously. Maps of galaxy motion that ignore the push from voids and focus only on the pull from clusters produce incomplete and inaccurate models. The dipole repeller also raised a new question. If one giant void behind us contributes this much to our motion, what about additional voids? What about underdense regions inside or near the zone of avoidance? If the hidden zone contains both massive clusters adding pull and extended voids adding push, the combined effect on our motion is more complex than any single structure explains. One confirmed finding from the dipole repeller research: the push and pull together trace what the team called the dipole axis, a line through space connecting the dipole repeller on one end to the Great Attractor and Shapley on the other. The Milky Way sits along this axis and moves along it, caught between the two extremes. That axis runs partly through the zone of avoidance. The structures anchoring both ends of the axis are partially hidden or poorly mapped because of the dust wall. Our galaxy is being steered along a path defined by structures we have only partially seen. What happens when that path continues? Where does the Milky Way go if it follows this axis for billions more years? And what waits at the far end of the pull? The Milky Way is not simply falling toward the Great Attractor. It is being squeezed along a cosmic corridor, pushed from one end and pulled from the other, moving along a path defined by two of the largest structures within 1 billion light-years of Earth. Understanding how these two forces combine requires thinking about gravity at scales that have no human equivalent. The pull from the attractor region, including the Norma cluster, the Vela supercluster, and the Shapley supercluster acting together, generates a gravitational acceleration directed toward the constellation Centaurus. The push from the dipole repeller generates a pressure directed away from the constellation Perseus in roughly the same direction. Both forces act along the same axis. Both drive the Milky Way in the same direction through space. This alignment is the reason our galaxy moves so fast. 600 kilometers per second is unusually high for a peculiar velocity. Most galaxies in relatively isolated environments move at speeds much lower than this relative to the cosmic background. The Milky Way moves at a speed that requires two major force contributions to explain. Either the pull is extraordinary or the push is extraordinary, or both are acting simultaneously in the same direction. Both are acting simultaneously. Researchers who modeled the combined influence found that neither force alone reproduces the observed motion accurately. The pull from the attractor region accounts for roughly half the observed velocity. The push from the dipole repeller accounts for roughly the other half. Together, they reconstruct the measured velocity of the Milky Way to within observational uncertainty. The geometry of this arrangement has one striking feature. The attractor, the Milky Way, and the dipole repeller are roughly aligned. Our galaxy sits along the axis between two extreme environments, one of the densest nearby regions of the universe and one of the emptiest. This positioning is not unique to the Milky Way. All galaxies in Laniakea participate in the same flow, streaming along the cosmic web toward the attractor while being pushed from the direction of the void. The combined motion is technically called a bulk flow. A bulk flow happens when a large region of space, containing many galaxy groups and clusters, moves collectively in one direction. The bulk flow centered on Laniakea is one of the largest and most studied in the nearby universe. Its existence confirms that both the push and the pull are operating across an enormous volume of space simultaneously. What happens to a galaxy caught in this corridor over billions of years? The answer depends on how the balance between expansion and gravity evolves. Today, the universe is expanding, and that expansion gradually works against the gravitational pull of the attractor. As the attractor region grows more distant over billions of years, its pull weakens. The dipole repeller, similarly, stretches and dilutes as the universe expands. Eventually, in the far future of the universe, both forces weaken enough that the bulk flow slows and stops. Galaxies in Laniakea will no longer stream toward the attractor. They will coast on whatever velocity they have accumulated, or slowly fall into whatever local concentration of mass surrounds them at that point. The window of maximum motion, when both push and pull operate at their current strength, is now. The Milky Way is moving faster today, relative to the balance of forces acting on it, than it will be at any future point in cosmic history. And at the far end of this motion, at the destination toward which our galaxy has been aimed for billions of years, lies an environment unlike anything in our current neighborhood. The Milky Way will never fully arrive at the Great Attractor. The expansion of the universe ensures that the attractor region keeps moving away faster than our galaxy can close the distance. But imagining arrival is useful, because the attractor region is already a place where galaxies have been arriving for billions of years. What happens to them tells us something about what the attractor truly is. Galaxies falling into the attractor region encounter an environment of extreme density. The Norma cluster, at the attractor's core, contains hundreds of galaxies moving at thousands of kilometers per second relative to one another. Hot gas fills the space between them at temperatures of tens of millions of degrees. Dark matter concentrations warp the gravitational landscape across the entire region. When a galaxy falls into a cluster this dense, several things happen. First, the galaxy encounters the hot gas of the cluster, called the intracluster medium. As the infalling galaxy moves through this gas, a process called ram pressure stripping tears the galaxy's own gas away from it. The gas a galaxy needs to form new stars gets blown backward like water off a moving boat leaving a trail of stripped material behind. Without fresh gas, star formation slows and eventually stops. Second, the gravitational environment inside the cluster distorts the infalling galaxy's shape. Close encounters with other cluster members stretch the galaxy's outer regions, pulling stars into long tidal streams that disperse into the cluster's general mass. Over hundreds of millions of years, the galaxy loses its spiral structure and becomes a smooth, featureless elliptical galaxy stripped of the organized rotation it had before. Third, in a dense cluster core, repeated close gravitational encounters called galaxy harassment accumulate. Each encounter is relatively minor, but over billions of years, the combined effect heats the galaxy's stellar disk, disrupting the organized motion of its stars. The galaxy becomes dynamically hot, which is the astronomical term for stars moving in disordered, elliptical orbits rather than smooth circular ones. If the Milky Way were to enter the Norma cluster, all three of these processes would begin immediately. Our galaxy's spiral arms, sculpted by billions of years of rotation and star formation, would start to dissolve. The Milky Way's gas supply, the raw material for every future star, would be stripped away. Within a few billion years, what had been the Milky Way would be recognizable only as a population of stars orbiting chaotically inside a larger cluster system. For any planets orbiting stars in that galaxy, the stellar density would increase dramatically. Stars would pass closer to one another more frequently, increasing the probability of disrupting planetary orbits. The night sky, from any planet's surface inside a cluster core, would be filled with galaxies visible to the naked eye, a sky overwhelmingly more active than what we see from Earth today. The cluster itself would keep growing. The Norma cluster today is denser than it was a billion years ago. In a billion years, it will be denser still. It is cannibalizing the galaxies that fall into it, growing at the expense of everything in its gravitational reach. The attractor region is not a destination in any comfortable sense. For galaxies that reach it, it is a point of no return. And yet the most disorienting fact is this. What we call the Great Attractor may itself be responding to something even farther away, something pulling the attractor region the way the attractor pulls us. The universe is not filled with galaxies scattered randomly like dust in a room. Galaxies organize themselves along structure. Long chains of galaxies stretch across hundreds of millions of light years, connecting clusters at their intersections, leaving enormous voids in the spaces between. Astronomers call this the cosmic web, and it is one of the most visually striking features of the universe at large scales. The cosmic web extends through the zone of avoidance. The dust hides it from optical telescopes, but radio surveys, infrared observations, and galaxy velocity maps have pieced together its outline behind the dust wall. What those surveys reveal is that the hidden zone is threaded with filaments connecting the confirmed structures on either side. Filaments are the highways of the cosmic web. Gas flows along them. Galaxies travel along them. Dark matter forms their invisible backbone, providing the gravitational skeleton along which ordinary matter arranges itself. Where filaments intersect, mass accumulates, forming the dense nodes that become galaxy clusters and superclusters. Several major filaments have been traced, running into or through the zone of avoidance toward the attractor region. One extends from the Perseus-Pisces supercluster, visible in the open sky, threading through the obscured zone in the direction of the Norma cluster. Another traces a connection from the Hydra Centaurus supercluster into the hidden zone. Both filaments channel matter toward the attractor region along paths that thread directly through the dusty band. The filament structure is important for understanding why the attractor region is so massive. Galaxy clusters do not grow only by capturing nearby galaxies. They grow primarily by accreting matter that flows along filaments from vast distances. A cluster at the intersection of multiple major filaments, like the Norma cluster, receives continuous inflow from each filament direction simultaneously. Over billions of years, this feeding mechanism assembles concentrations of mass that isolated clusters could never achieve. Radio surveys have identified candidate galaxies and galaxy groups along these filament paths inside the zone of avoidance. The galaxies line up in patterns consistent with filamentary structure, distributed along elongated chains rather than scattered randomly. Their redshifts, measured even through the dust, show that they share similar distances and velocities, confirming they are physically associated rather than coincidentally aligned on the sky. At the center of the web, where the major filaments converge, sits the densest node, and that node, based on the combined evidence from radio, infrared, X-ray, and velocity data, appears more massive than the Norma cluster alone accounts for. One specific filament, identified in surveys extending into the hidden zone, contains a chain of galaxy groups at the distance of the attractor region. The groups are unremarkable individually, but they sit along a line pointing directly toward the attractor core. If that filament is feeding mass into the core at the rate typical of similar filaments in open sky regions, it contributes significantly to the attractor's ongoing growth. Filaments in the zone of avoidance also explain one of the puzzling features of the dark matter maps discussed earlier. The extended dark matter concentrations that exceed what galaxy counts alone predict follow the expected path of filaments threading through the hidden zone. The dark matter traces the filament structure, which in turn traces the path of matter flowing toward the attractor. The web is alive behind the dust, and computer simulations of the entire universe, run without any knowledge of what specifically exists in the hidden zone, keep producing the same result every time they are run. Computer simulations of the universe start from the same conditions. The density fluctuations observed in the cosmic microwave background, the known ratios of dark matter to ordinary matter, the measured rate of cosmic expansion, and the laws of gravity and physics. From those starting points, simulations run the universe forward in time, letting gravity pull matter together, letting gas collapse into galaxies, letting galaxies cluster and merge. The simulations are built entirely from first principles. They do not know what sits inside the zone of avoidance. They have no information about the Norma cluster, the Vela supercluster, or the hidden zone's contents. They simply follow the physics. And they keep placing a massive structure in the direction of the great attractor. The illustrious simulation, one of the most detailed cosmological simulations ever run, produces large-scale flows toward a massive concentration in the direction corresponding to the attractor region. The Milky Way analogues in the simulation, galaxies with similar mass and position to our own, move toward that concentration at velocities similar to what we measure for the real Milky Way. The same result appears in the Eagle simulation, and in the Horizon simulation, each uses different numerical methods, different resolutions, different assumptions about certain poorly understood processes, like stellar feedback and black hole growth. They agree on the large-scale structure nonetheless. This convergence is significant. When simulations built on different architectures all produce the same large-scale feature, it strongly suggests the feature is a real consequence of the underlying physics rather than an artifact of any particular model. The universe, running forward from its initial conditions, appears to naturally produce a massive concentration in the direction of our motion. The simulations also predict the filament structure feeding into the attractor region. Multiple filaments converge on the high-density node in the simulations, matching the observational evidence for filaments threading through the zone of avoidance. The simulated cosmic web in that region looks like what the surveys, limited as they are, have been able to piece together. One particularly striking result from simulation studies, when researchers identify Milky Way analogues in the simulations and trace their history backward in time, those galaxies have almost always been moving toward the high-density region for several billion years. The motion is old, established early in cosmic history, and consistent throughout. Real-time measurements of our galaxy's motion match this pattern exactly. Simulations also suggest the attractor region is still assembling. Mass continues to flow in along filaments. The density at the core increases over time. In simulated universes similar to ours, the high-density region at the attractor location grows for billions of years before the expansion of the universe finally wins and the inflow slows. The gap between simulation and observation exists at the detail level. inside the zone of avoidance, where simulations predict specific cluster distributions and mass concentrations that surveys have not been able to fully confirm. This gap is the dust problem in quantitative form. The simulations say something specific is there. The observations say something is there, but cannot resolve exactly what. New instruments designed to pierce the hidden zone are being built specifically to close this gap, and the simulations point towards something else as well. A feature that emerges consistently in the large-scale structure at greater distances. A feature that connects the hidden zone to the deepest unsolved problem in modern cosmology. Every map of the universe has a hole in it. 1/5 of the sky, the band of the zone of avoidance, is incomplete in every galaxy catalogue ever produced. Astronomers fill in this region using interpolation, statistical averages from visible regions, and the limited data from radio and infrared surveys. The filled-in regions are educated estimates, not direct measurements. This missing data is more than an inconvenience. It introduces systematic errors into calculations that depend on knowing the full distribution of matter in the universe. The most direct impact is on calculations of large-scale structure. The cosmic web, the network of filaments, clusters, and voids spanning the observable universe, is mapped from galaxy surveys. Those surveys are complete only in regions the telescopes can see clearly. The zone of avoidance introduces a gap that forces researchers to stitch together the large-scale structure map with a blind patch in the middle. Correcting for this gap requires assumptions. Astronomers assume the structure inside the zone of avoidance is statistically similar to what they can see outside it. In regions away from the attractor direction, this assumption is probably reasonable. But in the direction of the attractor, where confirmed large-scale structure is already unusual, the assumption is precisely where it is most likely to fail. Mass concentrations inside the zone of avoidance contribute to the gravitational potential of the local universe. If those concentrations are systematically underestimated because of the dust, then every calculation that depends on the local gravitational potential carries a corresponding error. Estimates of how fast galaxy clusters should be moving, how dense the cosmic web should be in a given region, how quickly voids should expand, all of these carry uncertainty from the missing zone data. The problem extends to measurements of the Hubble constant, the rate at which the universe expands. The local measurement of the Hubble constant uses the motion of galaxies and standard candles like supernovae in our cosmic neighborhood. If the local gravitational environment is not fully mapped because of the zone of avoidance, the local Hubble constant measurement could carry a systematic error from the missing mass. This is not the primary cause of the Hubble tension, which involves a broader set of measurements and deeper theoretical questions. But it is a potential contributor that has been discussed in the literature, and it connects the zone of avoidance to one of the most debated problems in modern physics. The zone also affects measurements of the Milky Way's motion itself. Calculating the dipole anisotropy of the cosmic microwave background, which gives us our velocity through the universe, requires correcting for the gravitational influence of structures in our vicinity. An incomplete map of those structures introduces errors into the dipole calculation. Some recent studies have found that when improved estimates of the zone of avoidance mass are included in these corrections, the measured velocity of the Milky Way shifts slightly. The shift is within error bars, but it is consistent across multiple independent analyses. Better zone data would either confirm the shift or eliminate it, and either result would sharpen our understanding of the Milky Way's true motion. The hole in the map is a hole in our understanding, and it sits directly in the direction of the forces most responsible for steering our galaxy through space. Light, from the very beginning of the universe, passes through that hole every moment, and what happens to it along the way reveals something that no galaxy survey ever could. Every point on the sky emits a faint glow of ancient light. This is the cosmic microwave background, the radiation released roughly 380,000 years after the Big Bang, when the early universe cooled enough for atoms to form. That light has been traveling for almost 14 billion years, expanding and cooling as the universe grew. arriving at Earth today from every direction simultaneously. It passes through everything between its origin and our detectors, including the zone of avoidance, including the attractor region, including whatever sits hidden behind the dust wall. When this ancient light passes through a region with more mass than average, something specific happens. The photons of light fall into the gravitational well of the mass concentration as they approach it, gaining energy. As they climb back out on the far side, they should lose exactly the same energy they gained. Under normal circumstances, the effect cancels out perfectly, leaving no net change in the light. But the universe is expanding. While the photons are inside the gravitational well of a massive structure, the universe continues to expand and the well becomes slightly shallower. When the photons climb out, the well is a little less deep than when they fell in. They lose slightly less energy escaping than they gained entering. The result is a tiny net energy gain. The photons arrive at our detectors slightly warmer than average. This effect is called the integrated Sachs-Wolf effect. It is confirmed physics, measured in multiple studies by correlating the temperature map of the cosmic microwave background with the positions of known galaxy clusters and superclusters. In the direction of the zone of avoidance and the attractor region, the ancient light should carry the imprint of whatever mass sits there. Massive structures should leave a warm signal, voids should leave a cold signal. The pattern of warm and cold patches in the cosmic microwave background map in that direction encodes information about the hidden zone's contents. Researchers have studied the cosmic microwave background signal in the direction of the attractor region carefully. They find a signal broadly consistent with a large mass concentration in that direction. The warm patch in the ancient light map aligns with the known position of the Norma cluster and the broader attractor region, but the signal is larger than the confirmed visible structures fully explain. The warm patch covers a wider area on the sky than the known clusters account for. If the ancient light is accurately reflecting the gravitational environment it passed through, there is more mass in the hidden zone than current galaxy surveys have confirmed. The alternative is that the correlation between the ancient light signal and the attractor direction is partly coincidental, contaminated by other effects like the emission from our own galaxy's dust. Separating the ancient cosmological signal from the foreground galactic signal in that particular region of sky is technically demanding, and different analysis methods produce slightly different results. What is confirmed? Ancient light carries information about the hidden zone. What is a credible finding? The signal in that direction is slightly larger than confirmed structures explain. What remains an open question? How much hidden mass is responsible for the excess signal? There is another way the hidden zone leaks information. A subtler thermal signal produced not by ancient light but by the temperature of modern gas trapped inside the gravitational wells of galaxy clusters. And it has been detected coming from behind the dust. Hot gas inside galaxy clusters glows at millions of degrees. This gas, called the intracluster medium, emits X-rays directly, which is how X-ray telescopes detect it. But it also interacts with the ancient light of the cosmic microwave background in a subtler way. When photons from the cosmic microwave background pass through a galaxy cluster, they collide with the hot electrons inside the cluster's gas. These collisions transfer energy from the electrons to the photons, boosting the photons to slightly higher energies. The result is a small but measurable distortion in the temperature map of the ancient light coming from the direction of that cluster. This effect is called the Sunyaev-Zeldovich effect, named after the two physicists who predicted it in 1972. It has since been confirmed and measured for thousands of galaxy clusters across the sky. The effect is remarkably useful for finding clusters, because it does not fade with distance the way X-ray or visible light emission does. A cluster 10 times farther away produces a Sunyaev-Zeldovich signal of the same strength if its gas is equally hot and dense. Crucially, the Sunyaev-Zeldovich effect also penetrates the zone of avoidance. The distortion of the ancient light happens along the line of sight, regardless of whether dust lies between us and the cluster. Dust does not interfere with microwave radiation. A galaxy cluster behind the dust wall produces the same thermal distortion in the ancient light as a cluster in open sky. Surveys specifically designed to detect this effect have scanned the zone of avoidance. The South Pole Telescope and the Atacama Cosmology Telescope, both instruments optimized for measuring the tiny temperature variations in the ancient light, have observed regions overlapping with the hidden zone and found signals consistent with hot gas concentrations. Some of these signals correspond to the edges of known clusters whose halos extend into the dust band. Others appear in positions where no confirmed galaxy cluster has been catalogued in visible or infrared surveys. Researchers interpret these unmatched signals carefully. The most likely explanation for an unmatched thermal signal in the hidden zone is a galaxy cluster with hot gas that the dust has prevented optical and infrared surveys from fully identifying. The cluster exists, its gas is hot, and the ancient light carries the imprint of its temperature even though the cluster itself is invisible to conventional telescopes. The mass implied by some of these signals, estimated from the gas temperature and the size of the distortion, falls in the range of massive galaxy clusters. Several of the unmatched signals appear in the direction of the attractor region, overlapping with the part of the hidden zone where other evidence, radio emissions, X-ray glow, dark matter lensing, all point toward significant uncharted mass. The thermal signals from the ancient light are the most dust-immune evidence available for what sits in the hidden zone. They are direct physical imprints left by real hot gas on radiation that has been traveling for nearly 14 billion years. The dust cannot erase them. What they reveal is a picture of the hidden zone more complex and more massive than the confirmed galaxy catalogues suggest. And if the mass implied by those thermal signals is real, it changes how confident astronomers can be that they have correctly identified all the sources of our galaxy's motion. The growing sense in the field is that the attractor region is not static, it is changing, actively, right now, pulling in new mass from the surrounding universe. The Great Attractor is not a finished structure. Galaxies are falling into it today. Gas flows along filaments toward its core. Dark matter concentrations continue to deepen its gravitational well. The attractor region in 2 billion years will be measurably more massive than it is now. This ongoing growth is not a speculation. It follows directly from the confirmed physics of structure formation in the universe. Any massive concentration of matter with a gravitational well deep enough to draw in surrounding material will continue growing as long as matter flows toward it faster than the expansion of the universe carries that matter away. For the attractor region today, the infall of material is confirmed by the streaming velocities of nearby galaxies. Galaxy groups in the outskirts of Laniakea move toward the attractor region at measurable speeds. The inflow is ongoing. The cluster at the heart of the attractor, the Norma cluster, continues to receive galaxies falling along the major filaments threading through the hidden zone. Clusters in the process of active accretion show specific observational signatures. The hot gas in the intracluster medium develops asymmetries, with denser, cooler gas near the core and shock-heated gas at the edges where infalling material collides with the existing cluster atmosphere. X-ray observations of the Norma cluster show exactly these signatures. The cluster is actively accreting, with substructure in its gas distribution consistent with ongoing infall from multiple directions. The growth rate of the attractor region carries a direct consequence for our galaxy's motion. A more massive attractor exerts stronger gravitational pull. As the attractor grows, its pull on the Milky Way increases, meaning our galaxy's acceleration toward the attractor region, measured against all other forces, should increase slightly over time. The effect is small on human timescales, but it accumulates over millions of years. Simulations of structure formation predict that massive nodes, like the attractor, will continue growing until roughly 5 to 10 billion years from now. When the accelerating expansion of the universe finally overwhelms the infall, at that point, material moving toward the attractor but still outside a critical boundary will be pulled away by expansion faster than gravity can draw it in. Infall stops. The structure freezes at whatever mass it has accumulated by then. The attractor region today sits in a period of near maximum growth. The balance between gravity and expansion is still tipped toward gravity at the scales involved. The infall is ongoing. The structure is building. One implication for the hidden zone: if the attractor is growing, and if additional structures inside the zone of avoidance feed into it, those hidden structures participate in the growth process. Filaments carrying galaxies into the attractor pass through the obscured region. Clusters inside the hidden zone may be falling toward the attractor core themselves, adding their mass to the accumulating concentration. An entire assembly process, spanning hundreds of millions of light years and involving billions of stars, is occurring behind the dust wall right now. And in 2014, a faint signal pointed toward a structure behind the attractor that may be driving the growth of the entire system from even greater distances. In 2014, a team of astronomers published a study that expanded the known boundaries of the region pulling our galaxy through space. The study used a technique called peculiar velocity mapping. Researchers measured the velocities of thousands of galaxies spread across a large volume of the universe surrounding the Milky Way. They compared those velocities to the expansion rate of the universe, isolating the gravitational contribution, the extra push or pull beyond simple expansion. Then they traced those velocity vectors back to their sources. The analysis confirmed the known contributors: the Great Attractor region, the Shapley supercluster, the dipole repeller, but it also revealed residual motion that those known structures could not explain. Galaxies in a large volume of space showed a systematic drift that pointed not toward Shapley but past it, toward a region at much greater distances. The researchers described this as a possible coherent flow extending to distances well beyond the Shapley supercluster, in the direction of an even larger concentration of mass at the boundary of the observable nearby universe. The signal was faint. Peculiar velocity measurements carry significant uncertainty because distinguishing a galaxy's gravitational motion from its random orbital motion requires large statistical samples. But the coherence of the signal across thousands of galaxies, all showing the same systematic drift in the same direction, made it difficult to attribute entirely to measurement noise. What sits at the distance indicated by the residual drift? The surveys of that region are incomplete. At the relevant distances, beyond the Shapley supercluster, the galaxy catalogues thin out. The zone of avoidance still bisects that part of the sky, blocking the view of whatever sits in the most critical direction. And at those distances, even radio and infrared surveys have reduced sensitivity. What is known from other lines of evidence is that the region beyond Shapley, in the direction of our motion, contains additional superclusters. The Hercules supercluster and the Leo supercluster sit in nearby directions, though not precisely aligned with the flow. The Perseus-Pisces supercluster sits in a different part of the sky, and at greater distances, the galaxy distribution becomes statistically unusual in ways that suggest the large-scale structure there is still far from fully mapped. If the residual signal represents a real structure, it would need to be genuinely massive to exert a measurable gravitational influence across the distance to the Milky Way, something comparable in scale to Shapley, or larger, sitting at a distance where current surveys have not resolved it cleanly. This is a confirmed finding of an unexplained signal. The physical cause, whether a single massive structure, a series of superclusters acting together, or a feature of the large-scale structure not yet understood, remains a credible open question, and it connects directly to a possibility that cosmologists discuss carefully, because if it is true, it rewrites the scale of where we are in the universe. The observable universe is everything within a sphere roughly 93 billion light-years across, centered on Earth. This boundary exists because light from farther away has not had time to reach us since the Big Bang. Beyond that boundary, the universe continues, but we have no information about it. Inside the observable universe, matter is distributed according to the cosmic web. Galaxies, clusters, superclusters, filaments, and voids. At the very largest scales, the distribution is statistically uniform. No single supercluster dominates. The universe looks roughly the same in all directions when averaged across volumes large enough, or so the Standard Model predicts. A confirmed challenge to this uniformity exists: the large-scale flow of galaxies in our region of the universe. The bulk flow that includes Laniakea and extends across several 100 million light-years is larger in both speed and extent than the Standard Model of cosmology predicts for our location. Our galaxy moves at 600 kilometers per second. The bulk flow of which we are a part extends across an enormous volume. Standard cosmological models, calibrated to the cosmic microwave background and the overall distribution of matter, predict that bulk flows of this speed and scale should be rare. We happen to sit inside one. Some researchers have proposed that the bulk flow is driven by a concentration of mass near the edge of, or just beyond, the observable universe, something so large that its gravitational influence reaches inward across billions of light-years and pushes everything in our region in the same direction. This hypothetical structure has been called the Great Attractor's Greater Attractor by some researchers. The idea has a specific name in the literature. It is sometimes called the dark flow hypothesis. In 2008, a team reported detecting a coherent motion of galaxy clusters across billions of light-years, all flowing in the same direction. They interpreted this as evidence for a massive concentration of matter beyond the observable universe, pulling everything within our horizon toward it. The dark flow measurement was controversial. Other teams analyzed the same type of data and found no significant signal. The debate remains unresolved. The measurements involved extracting a tiny signal from the Sunyaev-Zeldovich effect across thousands of galaxy clusters, and the systematic errors in that extraction are substantial. What is confirmed? Our bulk flow is unusually large by Standard Model predictions. What remains a credible theory? A structure beyond or near the edge of the observable universe contributes to that flow. What is genuinely unknown? Whether the bulk flow signal extends to the distances required to support such a theory, or whether improved measurements will find it consistent with standard structure formation. If a structure beyond our observable horizon influences our galaxy's motion, it means we are embedded in something larger than we can map. The universe is not just bigger than what we can see. Its structure outside our window actively shapes what happens inside. That possibility connects to a problem in cosmology that has defined the last decade of observational astronomy, a discrepancy so persistent and so precisely measured that it suggests something fundamental about the universe may be misunderstood. The Hubble tension is the most discussed problem in modern cosmology. It is simple to state. Two different methods of measuring how fast the universe expands give two different answers. The difference is small in percentage terms, but it is statistically significant, and it has survived every attempt to explain it away as measurement error. The first method uses the cosmic microwave background. The temperature pattern of ancient light encodes the physical conditions of the early universe, including the rate of expansion. Applying the Standard Model of cosmology to those conditions gives a predicted expansion rate for the universe today. The second method uses nearby standard candles, primarily a specific type of exploding star called a Type Ia supernova, combined with the distance-velocity relationship of nearby galaxies. These measurements give a directly observed expansion rate for the universe today. The two numbers do not agree. The nearby measurement gives an expansion rate roughly 8% faster than the ancient light measurement predicts. 8% sounds small. In cosmology, an 8% discrepancy between two precision measurements either points to a systematic error in one of the methods or to new physics that the Standard Model of cosmology does not include. The zone of avoidance enters this problem through the local measurement. Calculating the local expansion rate requires knowing the distance and velocity of nearby galaxies with high precision. It also requires understanding the gravitational environment of our local universe, because the peculiar velocities caused by local gravity must be subtracted from the observed velocities before the pure expansion rate can be extracted. Subtracting the gravitational contribution of our local universe accurately requires a complete map of the nearby mass distribution. The zone of avoidance is a gap in that map. If the hidden zone contains significant uncharted mass in the direction of the great attractor, that mass contributes to local peculiar velocities that the standard correction does not fully account for. Studies that have attempted to estimate the zone of avoidance's contribution to local velocity corrections consistently find that improved zone data shifts the local Hubble constant measurement slightly. The shift is small, within current error bars, but it moves the local measurement in the direction of the early universe prediction. If fully characterizing the hidden zone reduced the discrepancy by even a few percent, it would be a significant result for the Hubble tension debate. Whether the zone correction alone can resolve the full tension is unlikely. The tension likely involves physics beyond a simple mapping gap, but the zone of avoidance is a real source of systematic uncertainty in the local measurement, and resolving it would tighten the constraints significantly. The Hubble tension may require new physics, an extension of the standard model that changes how the universe expands over time, or it may have a more mundane explanation in systematic measurement errors. Either way, completing the map of the nearby universe by resolving the zone of avoidance is a necessary step toward a definitive answer. Every attempt to understand our place in the universe leads back to the hidden zone. Even the fundamental question of how fast the universe expands cannot be fully answered without knowing what is behind the dust wall. What would a civilization inside the hidden zone see, looking back toward us? The zone of avoidance is obscured from our perspective. The dust in the plane of the Milky Way blocks our view inward toward that region, but the obscuration is not symmetric. From the perspective of a civilization inside the zone of avoidance, looking outward in various directions, the dust situation is entirely different. A planet orbiting a star inside the Norma cluster, for example, would sit roughly 220 million light-years from Earth. Looking toward us, those observers would not see a zone of avoidance. They would look out from their own galaxy, through whatever interstellar dust their galaxy contains, and see the full cosmic web of the universe spread before them. Our galaxy, the Milky Way, would appear to them as a faint smudge of light, one among hundreds of billions of galaxies visible across their sky. But their sky would be dramatically different from ours in one critical way. They sit inside one of the densest galaxy cluster environments known. Their night sky, the background behind the stars of their own galaxy, would be filled with visible galaxies. The concentration of galaxies in the Norma cluster means that thousands of galaxies would be visible without any instruments, each one a structure containing hundreds of billions of stars. For observers inside a dense cluster, the concept of intergalactic space would feel different. Galaxies would be neighbors rather than distant objects. The nearest large galaxy, for us the Andromeda Galaxy at about 2.5 million light-years, would be replaced by dozens of neighbors at distances of only a few tens of thousands of light-years. The gravitational environment inside the cluster would also affect what they could measure about the universe's expansion. Galaxies inside a dense cluster are gravitationally bound to one another and do not participate in the cosmic expansion the way field galaxies do. Observers inside the Norma cluster, measuring the velocities of nearby galaxies, would find a chaotic environment of high-speed motions dominated by the cluster's internal dynamics rather than the smooth Hubble flow we measure from our quieter position. Their measurements of the Hubble constant would require very different corrections than ours. Their local universe would be dominated by the cluster gravity, creating exactly the kind of peculiar velocity environment that introduces systematic errors into expansion rate measurements. Interestingly, those observers would see the Milky Way as a relatively calm, isolated galaxy inside a smaller and less dense structure. From their vantage point, we live in the quiet suburbs while they live in an extremely dense urban center. Would those observers wonder what is on the other side of the dust wall in their own galaxy? Almost certainly. Every galaxy has a plane, and every galaxy's plane creates its own zone of avoidance for observers inside it. The hidden zone problem is universal, not unique to Earth. But from inside the attractor region, looking outward toward us, they would have a clear view of the large-scale flow. They would see Laniakea flowing toward their position, They would see our galaxy as one of the many falling toward them. They would understand the great attractor in a way we cannot, because they sit at its core. What they could not yet tell us is what produces the pull from even greater distances that moves their supercluster itself. The standard model of cosmology has a well-tested framework for how structure forms. In the early universe, matter was almost perfectly uniform. Tiny density variations, quantum fluctuations amplified by inflation, seeded the first slight concentrations. Gravity amplified those concentrations over billions of years. Small fluctuations became gas clouds. Gas clouds became the first stars. Stars formed the first galaxies. Galaxies clustered into groups and clusters. Clusters assembled into superclusters. This process takes time. Gravity is slow. The bigger the structure, the longer it takes to assemble. Galaxy clusters of moderate mass form within a few billion years. Superclusters take most of the age of the universe to assemble fully, and the models make precise predictions about how massive a structure can be at any given cosmic age. These predictions have been tested repeatedly, and some observations consistently find structures that are more massive and more organized than the models allow at the cosmic age when they appear. The most striking examples come from observations of the early universe. Telescopes capable of seeing galaxies when the universe was only a small fraction of its current age have found massive, well-organized galaxy clusters that the models predict should not exist yet. These clusters are there, fully formed, when the theory says gravity has not had enough time to assemble them. If a megastructure behind the zone of avoidance were fully mapped and found to be more massive than the Shapley supercluster, the implications for structure formation models would be significant. Such a structure would need an explanation. Either the initial density fluctuations that seeded it were unusually large, pushing against the observational constraints on those fluctuations from the cosmic microwave background, or the structure assembled through a mechanism the standard model does not include, or the standard model's timeline for structure growth is wrong in ways that current observations have not revealed. Any of these outcomes would require revisions to the cosmological model. Revisions at that level would propagate through decades of work built on the model's predictions. Calculations of dark matter density, of the timing of galaxy formation, of the large-scale structure of the universe, all would need re-examination. The models have survived previous challenges, but each new observational constraint tightens the space available for the model to be right. Cosmologists describe this situation with a specific phrase: the model is under pressure. It works remarkably well across a huge range of scales and observations. But certain specific observations, massive early clusters, the Hubble tension, the unusually large bulk flow of our local universe, each push against its predictions in ways that have not been resolved. A fully characterized megastructure in the zone of avoidance, confirmed through the next generation of surveys, would add another data point to this growing collection of tensions. Whether those tensions add up to a crisis or eventually resolve into a refined and improved model depends on what the surveys find. And some of those surveys are already running. There is a deeper version of the zone of avoidance problem, one that does not depend on dust at all. Our solar system sits inside the Milky Way. We are embedded in the disk of the galaxy, roughly 26,000 light-years from the center, inside one of the spiral arms. This is not unusual. Most stars in a spiral galaxy live in the disk. But it means that looking along the galactic plane in any direction means looking through the maximum amount of galactic material simultaneously. Even if all the dust in the Milky Way were somehow removed, an observer inside the disk would still face a fundamental geometric challenge. The density of stars along the plane of the galaxy is orders of magnitude higher than the density above or below it. Looking through the plane means looking through a column of stars so numerous that their combined light creates a diffuse glow that makes it difficult to resolve individual faint background galaxies. Foreground starlight, foreground gas emission, and galactic radiation all compete with the signal from extragalactic sources on the other side. Dust removal alone does not solve this. The stellar density problem persists. The galactic center itself, a region of intense radiation, strong magnetic fields, massive star formation, and the supermassive black hole at its core, sits in the direction most obscured by the zone of avoidance. Looking through the galactic center at anything beyond it would require instruments capable of resolving extremely faint extragalactic signals in a region of sky dominated by some of the brightest astrophysical sources in the galaxy. This geometric limitation is permanent. Short of moving our entire civilization to a position outside the galactic disk, there is no vantage point from which an Earth-based observer could simply look through the plane of our galaxy and see the other side clearly. What changes over time is our ability to extract signals that cut through the noise. Radio waves are not scattered by stars the way visible light is. Gravitational lensing works regardless of stellar density. The Sunyaev-Zeldovich effect operates at microwave frequencies that the galaxy's stars do not produce. Each of these methods extracts information from the hidden zone through channels that the geometric problem does not fully close. But each method has its own limitations. Radio surveys can identify galaxy candidates but often cannot confirm distances without optical spectroscopy. Lensing maps require large numbers of background galaxies to build statistical precision, and stellar contamination reduces the usable sample in the hidden zone. Microwave signals are real but diffuse, and separating extragalactic signals from the galaxy's own microwave emission requires careful modeling. The zone of avoidance is genuinely hard. The combination of dust, stellar density, galactic center emission, and geometric depth makes it the most difficult region of the sky to study at virtually every wavelength. Some fraction of whatever sits inside the hidden zone may remain unresolved for decades, even with the best instruments currently being planned. This means the question of what anchors our galaxy's path through space may remain partially open for a long time. The instruments being built to answer it represent the most targeted effort in the history of astronomy to solve a single observational problem. The astronomical community has recognized the zone of avoidance as one of the defining observational challenges of modern cosmology. In the last decade, several major projects have been designed specifically to address it. The most powerful tool currently operational for probing the hidden zone is the Meerkat Radio Telescope Array in South Africa. Meerkat consists of 64 individual radio dishes spread across 8 kilometers of the Karoo Desert. Its sensitivity to radio emission from neutral hydrogen, the tracer that reveals galaxies behind the dust, surpasses any previous radio instrument by a significant margin. The ongoing Meerkat Zone of Avoidance survey has been systematically scanning the hidden band, detecting galaxy candidates that previous surveys missed, and measuring their redshifts to map the three-dimensional structure of the hidden zone for the first time with this level of precision. Early results from the Meerkat survey have already added thousands of galaxy candidates inside the zone of avoidance to the catalogue. The survey extends into the densest part of the hidden band, where previous instruments could detect only the brightest sources. Structures that appeared as hints in older surveys are now resolving into identifiable galaxy clusters and filaments with confirmed distances. The square-kilometer array, currently under construction in South Africa and Australia, will be the largest radio telescope ever built when complete. Its collecting area, spread across thousands of individual receivers, will give it sensitivity roughly 50 times greater than Meerkat. The square-kilometer array will be capable of detecting galaxies in the zone of avoidance at distances where current instruments struggle, extending the three-dimensional map of the hidden zone to cosmological scales that overlap with the Shapley supercluster and beyond. Infrared capabilities are advancing as well. The Nancy Grace Roman Space Telescope, expected to begin operations in the late 2020s, carries a wide-field infrared camera designed for deep surveys. Its near-infrared sensitivity will allow it to detect galaxies behind the zone of avoidance dust more effectively than ground-based infrared surveys, particularly in regions where the dust is thick but not at its maximum density. X-ray astronomy contributes through the Athena Observatory, a European Space Agency mission in development, which will conduct the deepest and widest X-ray survey of the sky yet attempted. X-ray emission from galaxy cluster gas penetrates the dust and provides direct evidence of massive concentrations inside the hidden zone. Athena's sensitivity will detect fainter and more distant clusters than any previous X-ray mission. For the thermal Sunyaev-Zeldovich signal, the Simons Observatory in Chile and the future CMB S4 project will map the ancient light with unprecedented resolution. These instruments will detect the thermal imprint of hot gas in galaxy clusters anywhere in the sky, including inside the zone of avoidance, identifying concentrations that no other instrument can confirm. Combining all of these surveys simultaneously, radio, infrared, X-ray, and microwave, will give astronomers a multi-wavelength picture of the hidden zone more complete than anything possible with any single instrument. The results of these surveys will determine whether the hidden zone contains a megastructure, whether the great attractor is fully accounted for, and whether the Hubble tension has a contribution from uncharted local mass. Everything the evidence has been pointing toward will either be confirmed or ruled out. The answer is coming. If the surveys confirm a megastructure behind the zone of avoidance, the consequences extend far beyond astronomy. The immediate scientific impact would be concrete. A confirmed structure larger than the Shapley supercluster, sitting inside or immediately behind the zone of avoidance, would require revisions to the standard model of cosmology. Structure formation timelines would need adjustment. The predicted maximum scale of gravitationally bound structures and the rate at which gravity can assemble mass would require recalibration against the observed fact of a structure too large to fit comfortably within current predictions. The revision would propagate. Dark matter models, which predict specific distribution patterns based on the standard framework, would be tested against the new structure's shape and mass. If the dark matter distribution inside the hidden zone differs from what the models predict, that would add another constraint to the already pressured question of what dark matter actually is. The Hubble tension might find a resolution, or at least a partial one, if uncharted mass in the hidden zone has been systematically biasing local expansion rate measurements. Correcting for the true mass distribution would shift the local Hubble constant value. Whether the shift is large enough to close the tension with early universe measurements depends on how massive the hidden structure turns out to be. Beyond the specific numbers, the philosophical impact would be significant. For most of human history, the assumption was that our position in the universe is average, a principle cosmologists call the Copernican principle. We are not at the center, we are not in a special location, we are one galaxy among billions. Discovering that the Milky Way sits along the axis between two of the most extreme gravitational environments within 1 billion light-years, one of the densest nearby concentrations of matter and one of the largest nearby voids, challenges a naive version of that assumption. We are not at the center of anything, but we are positioned in a cosmically interesting way, embedded in a structure shaped by forces that span hundreds of millions of light-years. Understanding those forces fully would change how humanity tells the story of where we are. The Milky Way is not floating freely in an undifferentiated universe. It rides a current. It has a direction. It has been aimed at something specific for billions of years, something that may be the largest structure within our observational reach. The confirmation would also sharpen the deepest question the evidence raises. If a megastructure exists behind the blind spot, what formed it? The answer pushes back to the very beginning of the universe, to conditions in the first fraction of a second after the Big Bang, when the density fluctuations that seeded all subsequent structure were imprinted on the fabric of space. Those conditions are observable today in the cosmic microwave background. If a structure of that scale requires initial conditions that the microwave background's temperature map does not clearly show, then either the microwave background measurements need reinterpretation, or the structure formed through a process not in the current model. Either answer leads somewhere new. The Milky Way has a blind spot. Something is inside it. And humanity is, for the first time, building the instruments capable of seeing what it is. Whatever the surveys find, the universe will be stranger and more structured than we assumed. It always is.